Imagine the universe as a story, written in a language of mathematics and energy, its plot unfolding over 13.8 billion years. Now imagine a single letter in that story, on the very first page, is changed. A tiny, insignificant alteration. And because of that one change, the ink vanishes from all the later pages. The chapter on galaxies never gets written. The paragraph on planet Earth dissolves. The final, precious sentence that is you, was never even conceived. Your entire existence is the postscript to a set of rules you had no say in. But what if those rules are too perfect? Too convenient? What if the story of the universe reads less like a random epic and more like a carefully crafted script, with you as the improbable main character? This isn't a comforting thought. It's the deepest and most unsettling puzzle in all of physics. Why not something else? Why are the fundamental numbers governing our universe so ridiculously, so improbably, perfect for life? This is the science audit. Today, we're putting reality itself on trial. The charge? The illusion of fine-tuning. This is going to be a deep dive. Get comfortable. Our verdict could change everything you think you know about your own existence. Let's open the case file. Alright, before we put our suspects on the stand, we need to establish the rules of the court. When we talk about auditing the universe, what are we actually looking at? You might hear people make dramatic claims like, if you change the speed of light, life would be impossible. And while that might be true, it's a sloppy argument. It's a rookie mistake. Why? Because the number we use for the speed of light, roughly 300 million meters per second, depends entirely on our human-made units of meters and seconds. An alien civilization using different rulers and clocks would get a completely different number. The physics wouldn't change, just the label. To conduct a true audit, we must ignore these human labels. We need to look at the numbers that have no units. Pure raw ratios. The universe's own internal settings. Think of it this way, the rules of chess are absolute. A pawn moves one way, a knight another. But the size of your chessboard? The material the pieces are made of? That's arbitrary. You can play chess on a giant park set or a tiny magnetic board for a plane. The game itself is identical. The dimensionless constants are the rules of the cosmic game. A recipe that says 2 cups of flour is meaningless without defining a cup. But a recipe that says 2 parts flour to 1 part water is a universal truth. It works on any planet, in any galaxy. These are the numbers we are putting on trial today. And our audit has identified 4 prime suspects, 4 dimensionless numbers so critical that if they were even slightly different, this investigation wouldn't have a detective. Let's meet them. Our first suspect is the most famous number in all of modern physics. It has a name that sounds like it's from a spy movie, alpha. The fine structure constant. Its value is simple, elegant, and deeply mysterious. It's approximately 1 divided by 137. Not 1/137th of anything. Just that. A pure number. The legendary physicist Richard Feynman once said that it's a magic number that comes to us with no understanding by man. All good physicists put this number up on their wall and worry about it. So what does it do? Alpha is the master volume knob for one of the 4 fundamental forces, electromagnetism. It dictates the strength of the handshake between light and matter, between photons and charged particles like electrons. Every time sunlight warms your face, every chemical reaction that powers your body, every single bit of data flowing through the device you're watching this on right now, all of it is being governed by alpha, at 1/137. It is, quite literally, the engine of the observable world. So let's do what a good auditor does. Let's stress test the system. What happens if we turn that dial? Let's crank alpha up a bit. Say, from 1/137 to 1/130. That's a 5% change. Electromagnetism gets stronger. What's the result? Absolute chaos. Inside atoms, the electrons are now pulled more fiercely toward the nucleus. More devastatingly, inside the nucleus itself, the electrical repulsion between protons gets stronger. A nucleus like carbon, with its 6 protons, might become unstable, unable to hold itself together. Heavier elements essential for life, like oxygen and iron, would be even less likely to form or survive. The periodic table, the entire toolkit for building interesting things, would be decimated. Chemistry would be a shadow of its former self. Okay, so let's turn the dial the other way. Let's make alpha weaker. From 1/137 down to 1/145. Electromagnetism is now feebler. The result? Just as bad. To create carbon and oxygen in the first place, you need stars. Stars are fusion engines, balanced on a knife's edge between gravitational collapse and the outward push of thermonuclear explosions. A key process for creating carbon is called the triple alpha process, where 3 helium nuclei fuse together. This process is a delicate quantum resonance. It works because the energies line up just right. Weaken electromagnetism, and that resonance shifts. The star's furnace can no longer efficiently forge the elements of life. Stars would shine, but they would produce a universe of mostly helium. A universe without carbon is a universe without us. Tweak the dial either way, and you snap the chain of events that leads from the Big Bang to biologists. The permitted range for alpha isn't a barn door, it's a keyhole. And our universe is threaded perfectly through it. One dial looking perfect is a coincidence. But in a cosmic criminal case, you look for a pattern. This brings us to our second suspect, a number that governs the very shape and scale of matter itself. Let's bring in our second suspect, the Proton-to-Electron Mass Ratio, known as mu. The name is technical, but the concept is beautifully simple. Picture a cosmic seesaw. In one seat sits the proton, the heavy, stable core of a hydrogen atom. In the other sits the electron, the lightweight, nimble particle that orbits it. The proton is about 1,836 times heavier than the electron. That ratio, mu, is our number. Why does it matter so much? Because this ratio dictates the fundamental rules of atomic architecture. It sets how tightly electrons are bound to a nucleus, which in turn defines the size of atoms and the length and strength of every chemical bond in the universe. It's the blueprint for how matter builds itself. Let's play with this dial. If you make the proton relatively lighter or the electron heavier, you change the ratio. Let's squeeze it from 1,836 to, say, 1,000. Electrons are now bound much more loosely. The very nature of chemical bonds would shift. DNA, that famously elegant double helix, relies on precise bond angles and hydrogen bonds of a specific strength. Change mu, and the DNA molecule might not hold together. Or it might be so rigidly bound it can't unzip to replicate. The delicate ballet of protein folding, where long chains of amino acids curl into the complex machinery of life, would fail. The lock and key mechanisms of biology would be broken. But the consequences go even deeper, into the very stability of matter. There's another particle, the neutron. It's slightly heavier than a proton. That tiny bit of extra mass allows a free neutron to decay into a proton, an electron, and a neutrino. This is crucial. But what if we tweaked mu? If we nudged the proton-electron mass difference, we could alter this delicate balance. In one direction, you could make the neutron so unstable it decays even inside an atomic nucleus. The universe would be left with only one element, hydrogen. In the other direction, you could make the neutron perfectly stable, even lighter than a proton. In the early universe, protons and electrons might have simply combined to form stable neutrons, leaving behind a universe with no hydrogen to fuel stars or form water. It is a stunningly delicate balance. The number 1,836 isn't just a random ratio. It's the setting that allows for both nuclear stability and a rich, diverse chemistry. It allows water to be water, and DNA to be DNA. The verdict on suspect number 2? It's just as suspiciously perfect as the first. We've audited the laws of the micro world. Now we zoom out. All the way out, to the beginning of time. Our third suspect governs the birth of all cosmic structures. Its name is Q, the Primordial Fluctuation Amplitude. Its value is tiny, about 1 part in 100,000. To understand Q, you need to see the universe's baby picture. It's a real photograph. It's called the cosmic microwave background. It's the afterglow of the Big Bang, and it shows us that the infant universe was an incredibly smooth, hot, dense soup of energy and matter. But crucially, it wasn't perfectly smooth. There were minuscule variations in density, tiny ripples, like the faintest whispers on the surface of a still pond. Q is the measurement of the size of those ripples. It is the cosmic seed from which all structure grows. Those regions that were 1 part in 100,000 denser than average had a little extra gravitational pull. Over hundreds of millions of years, they tugged on the matter around them. The rich got richer. These seeds slowly, patiently, magnificently grew into the vast clusters and superclusters of galaxies that dot our universe today. Our Milky Way galaxy, our sun, our planet, we are all the descendants of one of those tiny, primordial seeds. So, what if Q had been different? Let's imagine a universe where Q was much smaller. Say, 1 part in a million. The seeds are too weak. The universe expands so fast that gravity never gets a chance to grab hold. The cosmic soup just thins out into an eternal, featureless, cold, dark mist of hydrogen and helium. Utterly boring. A cosmic failure. No galaxies, no stars, no planets, no life. Now for the other, more violent alternative. What if Q was bigger? Just a little. 1 part in 10,000. Now the seeds are too powerful. Gravity is too effective. As soon as the universe begins, these dense regions collapse catastrophically under their own gravity, not into gentle galaxies, but into monstrous, primordial black holes, each potentially trillions of times the mass of our Sun. The universe would become a violent shooting gallery of galaxy-sized black holes, shredding and devouring any matter that dared try to form. No stable orbits, no quiet galactic suburbs, no 9 billion years of peace for life to slowly evolve. A cosmic mosh pit. Once again, we are on a tightrope. Too smooth, you get nothing. Too lumpy, you get a cosmic demolition derby. The number 1 in 100,000 seems to be the Goldilocks setting for a universe that is interesting, structured, and long-lived. We've covered matter, forces, and structure. This brings us to our final suspect. The one that haunts the dreams of physicists. The ghost in the machine. The cosmological constant, Lambda, better known today as dark energy. What is it? It's a form of energy inherent to the vacuum of space itself. An anti-gravity. A persistent, cosmic push that is causing the expansion of the universe to accelerate. Now here is where our audit turns from a mystery into a horror story. When physicists try to calculate how strong this vacuum energy should be, based on our best-tested theories of quantum mechanics, they get an answer. And that answer is wrong. It's not just a little bit wrong. It is the most wrong prediction in the history of science. The theory predicts a value for lambda that is 10 to the power of 120 times larger than what we actually observe. That's a 1 with 120 zeros after it. How big is that number? Let me try to give you a sense of scale. If you were to measure the size of the entire observable universe, from one end to the other, and your measurement was off by a margin of 10 to the 120, your error would be a billion times smaller than the width of a single proton. The discrepancy is a cosmic scream. It's a complete breakdown of our understanding. So why is this a fine-tuning problem? Well, if lambda were as big as theory predicts, the cosmic push would have been so colossally powerful that it would have ripped the universe apart less than a trillionth of a second after the Big Bang. Atoms would have never formed. Not even atomic nuclei. The universe would be an expanding void of disconnected, fundamental particles. Utterly sterile. Instead, the value we measure is exquisitely, bafflingly tiny. But it's not zero. It's small enough that it allowed gravity to dominate for the first 9 billion years, giving galaxies time to form. And only then did it gently start to take over, beginning the era of cosmic acceleration we find ourselves in today. This introduces another layer of strangeness called the coincidence problem. Why now? Why are we living in the very specific, transitional cosmic era when the energy density of matter and the energy density of the vacuum are even comparable? It's the ultimate riddle. Something is suppressing the cosmological constant by 120 orders of magnitude, but leaving just enough of it behind to be measurable. It's like stopping a cosmic tsunami, but allowing a single, perfect ripple to get through. This isn't just a dial set to a specific value, it's a dial set to a value so close to zero it defies all rational explanation. The case has been made. The evidence is on the table. For cosmic dials, alpha, mu, q, and lambda, each sitting on a value that seems outrageously fine-tuned for our own existence. A coincidence of this magnitude demands an explanation. So, let's bring in the 4 leading theories. The trial begins now. The first, and perhaps most popular, explanation in cosmology today is chance, in the form of the multiverse. It says, stop being so arrogant. You're suffering from a massive case of observer bias. You marvel at winning the lottery, but you ignore the trillions of losing tickets. The idea is that our universe is not the only one. It's just one bubble in an infinite cosmic foam of other universes, constantly bubbling into existence through a process called eternal inflation. Each of these bubble universes has its own Big Bang, its own control panel. And on that control panel, the dials for alpha, mu, q, and lambda are set completely at random. In the vast, overwhelming majority of these universes, the numbers are garbage. They are sterile, dead wastelands, universes that collapse in a nanosecond, universes ripped apart by a huge lambda, universes that are just cold, empty gas. There are no physicists in those universes to complain about the boring laws of nature. We find ourselves in a light-permitting universe for the same reason you find yourself on a light-permitting planet. You aren't amazed to be on Earth instead of Jupiter or Mars, because you simply couldn't be having this thought anywhere else. It's a selection effect. We didn't win a lottery. We just woke up on the one ticket that could support winners. It's an incredibly powerful and elegant idea. But is it science? The moment you invoke infinite, unobservable other universes, you hit some deep, philosophical problems. First, the measure problem. How do you make predictions when you're dividing by infinity? Depending on how you slice up the infinities, you can get literally any answer you want. Second, and far stranger, is the Boltzmann brain problem. If you have an infinite amount of time and space, strange things will happen. It becomes statistically far more likely for a single, conscious, self-aware brain, with all your memories, to pop into existence from the random chaos of the vacuum for just a moment, than it is for an entire, low-entropy, 13.8 billion-year-old ordered universe to form. If our current multiverse models are correct, the overwhelming majority of observers in the multiverse should be these freak, fluctuating Boltzmann brains. But we are not that. We are creatures evolved over billions of years in a highly structured universe. The theory predicts we should be something we are demonstrably not. This is a massive red flag. The multiverse might be the ultimate get-out-of-jail-free card, but it comes at a very high cost. If chance isn't satisfying, what about the opposite? Necessity. The idea that the cosmic dials aren't random at all, they are fixed. This explanation posits that our current understanding of physics, the standard model, general relativity, is just an incomplete shadow of a deeper, more fundamental theory. A theory of everything. And within the mathematical structure of this final theory, the values of our constants are not up for grabs. They are calculated. They must be what they are for reasons of pure logic and symmetry. Alpha has to be 137 for the same reason the angles of a triangle have to add up to 180 degrees. It's baked into the fundamental geometry of reality. In this view, the universe is not a lottery ticket, it's a perfect snowflake, with a unique and inevitable structure. Life, then, is not an accident. It's a built-in consequence of these unchangeable laws. This is the holy grail for many physicists. They spend their lives searching for this final, beautiful equation. Candidates like string theory and loop quantum gravity attempt to do just this, to unite gravity and quantum mechanics, and show us the hidden gears behind the cosmic clock. But there's a problem. A huge one. For one, after decades of work, we haven't found the theory. But more critically, our best candidate, string theory, seems to have backfired. Instead of one unique solution, it appears to allow for a colossal number of different solutions, 10 to the power of 500, at least. Each solution corresponds to a different vacuum, with different laws and constants. This doesn't provide necessity. It leads right back to the multiverse. It's called the string theory landscape. So the dream of a single, inevitable universe seems to be receding, not getting closer. The third possibility is the most humbling. It suggests the fine-tuning problem isn't a problem with the universe, but a problem with us. It's a failure of imagination. This is the misperception hypothesis. We are like a puddle of water that wakes up one morning and marvels, "Isn't it a miracle that this hole in the ground fits my shape so perfectly?" The puddle is committing a logical error. The reality, of course, is that the water simply took the shape of the container it found itself in. This theory argues that we are the puddle. We are carbon-based life, evolved on a watery rock, so we look at the universe and are shocked to find that the laws of physics are perfect for carbon-based life on watery rocks. But maybe life isn't such a delicate flower. Maybe it's more like water, able to take countless forms. Could there be silicon-based life swimming in the methane seas of Titan? Could there be sentient plasma clouds living in the atmospheres of stars? Could there be life forms that exist as complex electromagnetic patterns in interstellar space? If life can take a vast number of different forms in universes with wildly different physical constants, then the light-permitting range on those cosmic dials might be much, much wider than we think. The fine-tuning might be an illusion, born of our carbon chauvinism. This fits with the long, humbling history of science, which has consistently demoted humanity from the center of the universe. The problem? It is pure speculation. Until we find evidence of radically different life forms, we only have one data point, ourselves. And for our kind of life, the tuning certainly seems incredibly fine. And that brings us to the fourth and final explanation. The wild card. The one that used to be relegated to late-night dorm room conversations but is now being seriously debated by some of the world's leading minds. The simulation hypothesis. It's brutally simple. The reason the laws of physics seem fine-tuned for the emergence of complex, intelligent beings is because someone programmed them that way. The cosmic dials are not random, nor are they inevitable. They are parameters in a piece of code. A programmer in a higher-level reality set the variables, hit run, and our universe is the result. This elegantly solves the fine-tuning problem. It wasn't a coincidence. It was a design choice. The argument, famously articulated by philosopher Nick Bostrom, is a statistical one. If you assume that any civilization that reaches technological maturity will eventually create countless ancestor simulations, hyper-realistic virtual worlds of their own past, then it follows that the number of simulated conscious beings in existence will vastly outnumber the biological ones. Therefore, statistically, it is overwhelmingly more likely that we are one of the simulated beings than one of the original biological ones. It's a brain-bending, deeply unsettling idea. Could we test it? Maybe. Some physicists have proposed looking for clues, like a fundamental pixelation of spacetime at the smallest possible scale, or evidence that the laws of physics are computational cheats designed to save on processing power. But for now, it remains a philosophical argument, a cosmic ghost story that is devilishly difficult to disprove. So, after this deep dive, where does the science audit land? What is our verdict? The multiverse is untestable and potentially paradoxical. The deeper law remains a beautiful and proven dream that may not even lead to a unique answer. The misperception idea requires a kind of faith in unknown biology. And the simulation hypothesis takes us out of science and into metaphysics. The stark reality is this: there is no consensus. The fine-tuning problem is real. The data, the uncanny values of alpha, mu, q, and lambda are undisputed. This is a genuine, gaping hole in our understanding of the universe. The selection effect, that we can only exist where we can exist, is a crucial piece of logic, but it is not a complete explanation. It tells you that you are on the winning ticket, but it doesn't explain why any winning tickets were printed in the first place. What this audit reveals is that the boundary between physics and philosophy is starting to dissolve. The questions we are asking now are as much about the nature of existence, observation, and consciousness as they are about quarks and galaxies. The universe is forcing us to confront not just what we know, but how we know. Tonight, go outside. Look up at the stars. See the vast, silent darkness. Every point of light you see is a fusion engine, its fire governed by alpha. The stable ground beneath your feet is made of atoms held together by mu. The grand, spiral structures of the galaxies in that darkness are echoes of Q. And the very fabric of that darkness, the space between everything, is alive with the silent push of Lambda. You are not an observer looking at the universe. You are a localized, temporary pattern woven from its deepest rules. You are the universe's way of knowing itself. The question of fine-tuning is not an abstract academic debate. It is the universe holding up a mirror and asking us, the improbable witnesses, what we see. The wonder is not that the story is so strange, but that we are here at all to read it. So, the science audit is turning this over to the jury. We've audited the 4 big theories: the multiverse lottery, the inevitable deeper law, our own cosmic misunderstanding, and the simulation. This is no longer just physics. It's a cosmic conspiracy theory. So which one do you find most convincing? Which one resonates with you, and which one keeps you up at night? Drop your verdict in the comments below. Let's see which theory wins the court of public opinion. And if you feel like your grip on reality is now sufficiently loosened and you want to explore more of these fundamental audits, you have to click the video on your screen right now. I promise it will take you even further down the rabbit hole. For your daily audit of existence itself, make sure you subscribe to the Science Audit. Our investigation has only just begun. Thank you for watching.